to the Quantum Feedback Loop. I'm your host, James Myers, and I also publish The Quantum Record, which features the latest in science and technology. It was a privilege to speak with Deirdre Haskell about the world of mathematics and its pivotal role in the latest scientific and technological developments. Dr. Haskell was recently appointed director of the Fields Institute for Research in Mathematical Sciences, where she previously served as deputy director. Dr. Haskell is also professor of mathematics and statistics at McMaster University. For someone like me who isn't a mathematician, it's fascinating to learn how mathematics provides a basis for so much of what the world now relies on, including GPS navigation, medical and astronomical imaging, modeling for climate change and finance, and artificial intelligence with its large language models like ChatGPT and many other functions. Based at the University of Toronto, the Fields Institute brings mathematicians from around the globe together to explore new frontiers for knowledge in an increasingly mathematical world. Deirdre provides a clear overview and many examples of how mathematics is shaping our lives. And after speaking with her, I'm even more intrigued about the potential for mathematics to engage with a broad range of people and disciplines in advancing science and knowledge. I hope you take as much from the discussion with Deirdre Haskell as I did.
Welcome to the Quantum Feedback Loop podcast. Really great to have you here.
Thank you, James. It's really great to be here.
I'm wondering if you could just tell us a little bit about your work and background as a mathematician and what brought you to the fields.
Yes, so my mathematical work, I'm a mathematical logician, which means I study the reasoning processes that we use in mathematics and then use what we learn from that study to apply it back to particular problems in mathematics. So I'm both studying what we're doing how we think mathematically, and also that gives us more mathematical information about particular mathematical structures.
Well, it's really interesting. And so what brought you to the fields?
I'm a professor at McMaster University, and as such, being a part of the Fields Institute community, over the years, I've participated in many events at the Fields Institute, and I've organized events at the Fields Institute. And so when the opportunity came up to apply for the deputy director position and then the director position, it was a way of giving back to the community, being able to run the Fields Institute, which is so much a part of the lives of mathematicians in Ontario.
Wow. And I understand it's a bit of a family thing as well.
That's right. My late husband was also the director of the Fields Institute. 2012 to 14, I think, were the years.
Oh, okay. So the Fields Institute is named after John Charles Fields. I'm wondering if you could just tell us a little bit about what he did, the 1924 conference that he set up in Toronto, and the Fields Medal, which is named after him.
Sure. So John Charles Fields was born in Hamilton and went through school and then came to Toronto to go to university. And studying mathematics at the time, there was not much opportunity for doing advanced mathematics in Canada. So he went to Johns Hopkins University in Baltimore. And then really, if one wanted to know what was going on in mathematics at that era, one had to go to Germany to study with the greats in Göttingen and to Paris to study with people there. And so he spent many years traveling around Europe, learning, meeting lots of people, learning languages, learning lots of mathematics. And then he brought all of that back to Canada and was a professor at the University of Toronto. In 1924, or coming up to 1924 rather, there's an event called the International Congress of Mathematicians, held every 4 years. And in the era between the two wars, there was a lot of tension in Europe between people from different countries who had recently been at war, and whether they could bridge that in order to come back together with mathematics. And John Charles Fields really saw mathematics as a way of making connections between people. He wanted to bridge the divide between the French mathematicians and the German mathematicians and the Americans and the Canadians and everybody else, to say we need to come together as a community, and mathematics is one way to do that. So he brought the 1924 Congress, the International Congress of Mathematicians, to Toronto in order to hold it here. And this was a really big moment for Canada in its scientific and intellectual development. It was an opportunity for the country to see that we had more to offer than just our natural resources. We also had the intellectual resources of our people. And making that move into doing fundamental research represented a big step forward. So For example, in order to produce the proceedings of the international conference in which people published the papers that they had presented, John Charles Fields had to work with the University of Toronto Press in order to create the mathematical typesetting, which had not even existed until before that time in Canada.
And so how many people would have attended the 1924 conference?
I think that there were, I'm going to forget now, maybe 400.
Well, it's a
Yes.
lot, yeah.
Yeah, it was very exciting, and people came from a long way away.
Yeah.
And then normally at a conference, you might have an afternoon when there's a little excursion somewhere. People were coming a long way away. They did an excursion to Banff.
Wow. And this is back before the jet airplanes.
Yes, yeah, they took the train across the country.
Wow. Were there any big names that we would recognize at the conference?
No, I don't remember any.
Right. And then the Fields Medal, when was that established and named after him?
Right. So after the Congress, John Charles Fields had the idea that there should be some kind of recognition for great work in mathematics. And he especially wanted to recognize the not just work that people had done, but their potential for future work. And so there was the idea of a medal which would be given to young people with a potential for future work. The medal was not actually awarded until 1932, which was after Fields had died. And it was not, in fact, his request that the medal be named after him. But the initial funding for the medal was given in his will, and possibly with some leftover money from the Congress.
Oh, wow. Okay. And so the Fields Medal is one of the top awards in mathematics now. It goes to the younger mathematicians, doesn't it?
That's right. So there's this rule that it has to be awarded before the individual's 40th birthday.
So in terms of the Fields Institute, it was, I guess, founded, I think, at the University of Waterloo in 1992. So this is 33 years, I guess, later. So can you give us a bit of an overview of its evolution over that time?
Yeah, so I'm not sure it's quite correct to say founded at the University of Waterloo. There were a group of people, including people from Waterloo, Toronto, McMaster, who came up with the idea that Canada should have its own mathematics research institute. And an institute for mathematics is a place where we bring mathematicians together from all over the world to talk to each other in order to facilitate the opportunity to spark new ideas, to make serendipity happen. And once this idea came forward and a lot of people had agreed that it should happen, then there was the question of where it should be located. And it was initially located in Waterloo. And then there was an international committee formed, and various Canadian universities, or I guess Ontario universities, put forward proposals for what they could offer in order to host the institute at their university. And the international committee went around and visited all the universities and studied all of the potentials for what were being offered. And this site here on the University of Toronto won, partly because University of Toronto agreed to build us a building. And so we have this beautiful building that we have, which was expressly designed to encourage mathematical collaboration.
Are there other institutes like this around the world?
There are. I think there was a kind of a period when institutes were happening.
Right.
Of course, the original one is the Institute for Advanced Study, but it's a little bit of a different model because they have permanent members. We are more like the Mathematical Sciences Research Institute in Berkeley, California, which is now called SL Math. And they're a similar model. We host events, we hold short-term events like workshops and conferences, but also more importantly, we hold long-term events. Our long-term events are 4 to 6 months long, in which we bring people together who are from all over the world who are thinking about the same research area. And by being here together, sitting in adjacent offices, talking to each other, holding seminars, you get all sorts of exciting new ideas, which would not have happened if people were not in the same place.
Wow. And so is there a primary focus or offering of the Fields Institute?
We do mathematics understood in its broadest possible sense. So we want to do pure math, we want to do foundational research, we also want to do applied math, we want to do math in context, we want to do math applied to all the different areas in which mathematics is playing a role.
And are there mathematicians who are attached to the Fields Institute in any way around the globe, or is it kind of, as needed or as desired?
Because we have a changing program, then the cast of people changes all the time. The permanent people, and actually that's not even correct, not permanent. We have two academics, the director and the deputy director, who have institutional affiliations elsewhere, but come in order to put their time into trying to run the Fields Institute. But those roles change on a regular basis. And otherwise, people will just come for a semester to be a part of the community that we have here.
And you do have public events as well. And so one of which was the symposium that was held back this past August, celebrating the 1924 Congress. And I was lucky to attend that as a non-mathematician. How did that go? Like, what were the outcomes of it? How many attended? Tell us a little bit about that.
Yeah, so indeed, 2024, we said it's 100 years since 1924. Let's make a celebration out of this event. We had around 150 people here. Our speakers included some of the top mathematicians from around the world, including, I think it was 6 former Fields medalists that we were happy to welcome back here. We had some of the talks were, we have in mathematics a tradition of something called a colloquium, where you ask rather famous people to give talks which are supposed to be at a level accessible to somebody at least outside of the research area. So maybe to a graduate student in mathematics. And that was the level that we were targeting in the talks that were given there. But we also had some events which were more open to the general public. You didn't have to have an undergraduate degree in math in order to understand some of what we were talking about. And we do try to reach out to the public in that way because it's important. We want to make research happen, and research happens by being at the very top level, talking about things which very few other people understand. You might say, oh, I'm upset because I can't understand it. But I say, well, I can't understand it either, to be honest. But also, it's also important that we are communicating to the world why what we're doing is important. And that's why we want to hold events like we had the panel discussions in which people talked about a little bit more generally about the research area and where it's going, or what has been the impact of some of the Fields medals and their research and what change that made to the research over time. And we also talked about the ways in which mathematics might change in the future, especially when we have machine learning and AI and automatic theorem proving. What difference is that going to make to the way that mathematicians do mathematics, the way that the outside world understands the mathematics that we're doing? And possibly there's always the question we're asking each other, is there going to be a time when an AI can do mathematics better than a mathematician? I mean, we now see that an AI can play chess better than a top chess player. Does the same also apply to mathematics? We really don't. It's not there yet.
Yeah.
But we don't know about the future.
Yeah, well, interesting. And I do want to talk about AI and mathematics in a little bit. I do remember that discussion about mathematics of the future. It was a good one. And I guess people left that symposium having made new connections and maybe even now working together. One thing that really struck me was how many different areas of mathematics there are. Algebraic geometry and analysis. And I can't even remember all the names now. So I guess it's a question maybe of tying a lot of these areas together, is it? Or making one area helping to understand the other area? Like there was the mathematical physics, for example, I remember. And so there was some talk where there's a different basis of understanding, I guess.
Yeah, it's really fascinating how you have different areas of mathematics just branch off from each other, and you have some kind of concept that you can explore into great depth, but then they come back together again. And so if you look at the sort of the tree of the growth of mathematics, it's not a tree at all because things keep coming back together and crossing each other. So one of the recent Fields medalists was given to Jun Hu, who, for his really exciting work, which was bringing together algebraic geometry on the one hand and combinatorics on the other hand. Now, those are two disciplines which seem like they're totally different. Combinatorics is about actually how do you arrange, you have colored beads in 3 different colors and you want to put them in a circle. How many different ways are there to do it? this is it's very much about counting. And algebraic geometry is about a very, one could say, a very abstract idea. You look at a polynomial equation and you look at the set of solutions of that polynomial equation and you ask what shape they make. And that shape could be a shape in the plane or in space or in complex space. So instead of looking at just real numbers, but you look at complex numbers as well, and then you ask what shape it forms. And so they seem like they're totally different areas. And yet June Hu was able to bring them together in a way to use the concepts from algebraic geometry in order to understand some conceptual questions in combinatorics. And it's when it starts to come together that it gets really exciting. And so you can have very abstract parts of mathematics which are interacting with each other, but then you can also have very abstract parts of mathematics which suddenly become relevant to something which seems like it's very concrete. And then you get something like topological data analysis. You have these ideas from topology, which are just very abstract ideas about shapes. And then you have very concrete questions about, I look at this data and I want to know what's cause and effect. And yet somehow the topological ideas can answer some questions about the data. That's just amazing.
Yeah, no, really. And what really struck me, actually, it was on the first day, I guess, of the symposium, was the talk about the Langlands program, which is largely, I understand it, is an attempt to tie mathematics and geometry together. And I guess back almost around that time, there was a major advance in the connection of geometry to mathematics. So that really struck me as one area. I guess, is that a major area that a lot of mathematicians are researching?
Yes, I would say that. So the Langlands program is a Langlands had this idea of a way to move forward, and he set out a description of how it might go without necessarily actually proving anything along the way, but was an understanding of the way the ideas might develop. And it's, yes, as you say, it's tying together algebraic questions, kind of in number theory, with geometric ideas. And so what's called the Geometric Langlands program has just recently had a very exciting advance. And we're kind of watching to see what might go forward there.
Oh, yeah, interesting. So another example of how different branches of mathematics are starting to converge. So maybe to talk about the practical applications of mathematics for the everyday listener who might find it incredibly complex or mysterious or frightening, if we can put it in context of, first of all, in our everyday lives, I guess there's mathematics in shapes that we look at, mathematics in architecture. I think you'd mentioned something about aesthetics.
Yes. So I was thinking while we were getting set up here about your arm here, the robot arm, really, which is holding the microphone. And when you want to think, when you're designing such a thing, you ask yourself, what kind of range am I going to get out of this? And we have here, 3 or 4 joints, which each have a certain angle that they can produce. So that's that angle at which you put it, that gives us 4 pieces of information. Those are 4 really independent pieces of information. So that's already in a 4-dimensional space. And then there's also the rotation. So that's another piece of data. And then there's the length of each of those arms. So when you're trying to design something like this, you have to think about that gives you a 6-dimensional object or a 6-dimensional shape, which you have to optimize so that it will reach the area that you want it to reach. And then we look at that shape and think, well, is there some part of the space that it's not going to reach? Like the microphone is not going to pick up the sound because it's at a certain angle. And so then you're looking at the topology of that shape. So something which you would think of as being a very practical industrial type of design problem involves all this mathematics, and it involves mathematics which is not just the mathematics that we can see, 3-dimensional space. It's a 6-dimensional space which we can't visualize anymore. And so we need to use mathematical tricks in order to understand that shape, in order to well design this object.
Yeah, interesting. So the industrial design aspect of it is maybe employing a lot of mathematicians.
I hope.
Yeah. Yeah.
Of course, we do need to teach our mathematicians to think about industrial design as well as the pure mathematics, but also the applications of it. Yeah. And not every individual is going to do every different thing.
Right. Now, I guess there's some other examples. Tell us a little bit about medical imaging.
So medical imaging, yes, you have a similar thing. You say you're doing an ultrasound imaging. You send out a signal and you get a message back. And the ultrasound technician just sees an image. But the question is, how was that image created? And so what we have is that if you're sending out the signal, there's a function which says there's this shape that's reflecting the sound. And that function is telling you what that shape is. Then you get the signal which comes back. That's an inverse function. It's a function, it's like an undoing function. And based on what information comes back, we need to create the image of what's out there. And there's a concept called a radon transform, which is invented by somebody named Radon, who was just thinking about, how do I do inverse functions? Do they exist? How could I calculate them? He wasn't thinking about ultrasound technology. It didn't exist. He was just thinking about this theoretical problem. And yet what we do is we use exactly that in order to create that image. And then, so you use a piece of theoretical mathematics, and then somebody comes along who understands that theoretical mathematics and can write the computer program, which will then be encoded into that ultrasound machine, which gives you an image.
Actually, I imagine that sounds similar to the way they do astronomy now, in terms of giant James Webb Telescope is seeing infrared data, but it's just data. It's not like it's seeing planets directly. And so it's taking the data and kind of recombining the points of light or the points of energy into an image.
Absolutely. Yep. Exactly the same.
Interesting. Data analysis is another one that maybe if you could talk a little bit about that.
Yeah, so there's the whole field of statistics, which is about understanding data and what information you can deduce from it and with what level of confidence. And the discipline of data analysis is using all of those methods of statistics. And it has to think about the statistics that goes into it, but also how you communicate it. So you have a bunch of data. Do you communicate it with a pie chart, a bar chart, but all sorts of other ways of communicating data. So there's the communication level, there's the context in which it takes place, and then there's the mathematics that goes into understanding it. And so this whole, that I mentioned the words topological data analysis, you have something which has thousands of different variables, which may be going into what perceived result you're seeing. You're trying to understand the process of human aging, and there's so many different factors that go into it. And you have to try to understand which of those are actually independent from each other and which of them are trying to affect each other. So by looking at the shape of the data, you can try to use topological information, which will tell you, is this really 1,000 independent variables, or is it actually really only 200? Wow. And maybe if it's only 200, then we can do something to affect those, or see how they're interacting.
Yeah, and certainly data, I guess, is how the world is run now. So I can imagine all of those correlations, I guess, and permutations of the data. So is it really looking at probabilities?
Well, certainly probabilities, yes. I mean, probability is underlying the notion of statistics.
Right. And then there's mathematical modeling. There's infectious diseases we saw during COVID, and we saw predictions about how fast it would spread. And I guess was a mathematical exercise. There's finance, there's climate. Maybe if you could talk a little bit about those.
So in so many different things, anything which is changing with time, we try to understand the function which will tell us what it will look like after a certain amount of time. And in order to understand what that function is, we look at what's making it change. So the infectious disease modeling kind of is a natural one. We think about how many people are infected, and then how they interact with people who are not infected, and then how many of those people will get sick. And so that gives us what's called a differential equation. We have a function which says how many people are infected right now. And then we have the rate of change of that function, which is a derivative. And then there's how the derivative, the rate of change, is related to the size, the value of the original function. And so we have this relationship between the function and its derivative and some other derivatives, and we write all that down, and that's a differential equation. So that's describing how this system is changing. But then we have to ask, well, what's the solution to the differential equation? That is, what is the function which behaves according to this information? And we can write down a differential equation, but we can't always solve it. And so solving the equation then becomes, so the modeling part says, okay, I've got this idea that everything's related in this way. What are the parameters? So I know it's related, the derivative is something related to the function, but what's the constant? And so I use the data that I have to try to tell me what that constant is. And that's the modeling process. And then we try to solve that differential equation and read it off so that we can know what's going to happen 10 days from now. But everything that changes has a differential equation. Everything.
Yeah, I guess calculus basically, right?
Yes, and then there's a calculus, and we use all those techniques from calculus to try to find out what's going to happen.
Yeah, really interesting. And I guess climate, with the rapid change in climate now and the effects that are becoming harder to predict, I guess that's one area where mathematics is really heavily used now.
Absolutely. So, of course, in the climate, this is an example where we have all these thousands of variables, and they're interacting in very complicated ways, and we're trying to write all of them down and then decide which ones are important and try to solve all those equations, which will tell us what's going to happen. And there's so much information, and we don't know all of it, and we don't know how things are related. But this is really a nice example where mathematicians have to interact with scientists and all sorts of other disciplines. We need to know how the atmosphere behaves, so that's given to us by atmospheric scientists. We need to know what's happening in the oceans. So we need to know how the flow, the aerodynamics of, there's a coal plant over here and it's emitting carbon dioxide, and how fast does that flow over the entire atmosphere? And the mathematics tries to take all of that information so that it can correctly model to write down the right differential equations. And then you have this incredible mess of all these equations that you're trying to solve, and you probably can't solve them. They're too big, they're too complicated. So then you try to do approximate solutions using numerical methods. And then you need to know, to understand, well, I'm using a numerical method, it's giving me an approximate solution. How approximate is it? What are the error bounds? And then use the error bounds to say, well, if the error bounds are too big, then it would give you the answer. It could be anything from the world's going to end tomorrow to what are we worried about?
Yeah.
In that case, it's not particularly useful.
Yeah, and I guess, a lot of people conveniently want to dismiss what we know about climate change because I guess it's so complex and there are so many variables. But I guess the key is just to keep working at it and to make sure that you're accounting for the variables, looking at the differences, the errors over time, and just keep getting it more precise. Is that?
Yes, and also trying to communicate what we're doing and what's the reliability of what we're doing, and how, even if we can't get exact answers, we can still get information which can help guide what we're doing now.
And finance is one area where I have some experience, and not that I do the calculations myself, but in terms of calculating things like options values and futures values. I guess that's mathematically based on past performance and correlated securities and all of that sort of thing. So I guess it's a big field in finance as well.
Yeah, I think it's more a statistical analysis rather than using past behavior. In fact, I think it's saying, we've got all these thousands of different possible stock options. What might change as we move forward, and what's the probability of the way that they interact? But I actually don't know anything about finance, so I shouldn't try to address that.
Well, we won't go too far into finance, but the big one I think you mentioned to me now is the, AI, but the large language models like ChatGPT, Gemini. And so I understand you've said that that's a big area of mathematics now. If you could maybe just explain that and neural networks and how all of that kind of...
Sure, that's a big topic. So there's the mathematics that goes into designing an LLM itself, which says you look at all of this data, absorb all of this information, which is lots of text that's written out there, and you can do probabilistic assessments of, if the first three words were this, what's the likelihood of the next answer? And then you have a mathematical assessment which is called following the gradient, in order to find the best possible route through the list of all possible answers. So the mathematics that goes into that is not terribly hard. It's kind of like second or third year level undergraduate mathematics, which I'm not trivializing what's going in there's a lot that goes into it, and they're very complicated. But then there's another question, which is the mathematics that explains how it works. The mathematics that might say, well, why does an AI hallucinate? Or just trying to make predictions about how the AI will behave in itself. And that is something that I think is a really big question, and the really hard question. I think it's going to involve having a lot of really new ideas in mathematics to try to explain what's going on there.
So I know people are talking about limitations to these LLMs. Maybe they're kind of reaching their limitations now. And I guess the continued hallucinations where they're just simply the output doesn't relate to the input. I guess that's what the hallucination would be.
Yes, or not so much doesn't relate, but relates in a very strange and unexpected way.
And so I guess in terms of predicting word relationships, the LLMs are using huge amounts of data. And I guess really an issue is the quality of the data. Do mathematicians get into the quality question, or is that kind of another area?
Well, it's probably not the mathematician who's thinking about the quality of the data, but certainly it's true that every time you generate more data, then if you put out bad data as well as good data, then maybe it's more likely that there's going to be more of the bad data, and then the LLM reacts to what the data there is in a probabilistic way. If there's more of the bad stuff, it will follow the bad stuff because that's the way it's designed to work. I think it kind of a different question to think about, if you want to think about artificial intelligence overall, is that using the LLM is just one way in which you might generate an artificial intelligence. And it doesn't have to be the only way. Maybe we'll do something different to try to make a computer which can think, and maybe there will be something, it will go in a different way. So we don't have to think about, understanding LLMs is not the last word on artificial intelligence.
And yeah, we've talked here about a number of different ways that math relates to everyday living, although somebody using a ChatGPT won't appreciate necessarily all of the mathematical functions that goes into making it work. But certainly looking around you at the world of shape, there's mathematics embedded in that. And certainly in any computerized application, whether it's the phone or the computer or GPS, for example,
you're not thinking about the mathematics that goes into the GPS every time you use it, and you don't need to. But it's nice if you're aware that there's some interesting mathematical theory that goes going on there.
Yeah, and physics as well. Yeah, it's really fascinating to think about. So in terms of in the mathematical world, the frontiers of mathematics, are there any kind of major topics that are now being looked at, focused on, where a lot of people are just really focusing efforts to see if they can make some sort of breakthrough?
I think this whole question of the mathematics of AI and how AI is or is not succeeding in doing mathematics is a very big question, very big open direction for a lot of mathematicians to look at, and to bring all their different pieces of knowledge together in ways to see how we can understand what's going on. I think that might be a really big open challenge for, I don't know, the next however many years.
Yeah. And so when Roger Penrose, for example, says that consciousness is not a computable function, I think is what he's saying, does that mean that it's, in his view, it's not mathematical?
No, in his view, it's not algorithmic.
Okay.
I actually had a very interesting conversation just yesterday about whether or not the human brain can be considered to be computable, or the activities that it does are producing computable functions. I don't think I have an opinion on what the correct answer is to that.
Yeah, I think few people dare to venture in that. As a quest for AGI, if it's possible, and I'm on record saying it's not possible, but in the quest for AGI, I guess we're looking for that. So in terms of upcoming events at the fields, is there anything special coming up or any plans for the next few years?
Well, we want to continue doing what we do well, which is making opportunities for mathematicians to get them together to have ideas. We are thinking about a Path of AI program in some way, trying to bring, as I talk about this, I learn more and more people who are interested about it and thinking about the problem from different directions. And I think that to bring together the people in Ontario and around the world who are thinking about these questions at the Fields Institute would be a really exciting opportunity.
Yeah, for sure, for sure. And then I guess there's the upcoming Mathematics Congress in 2026.
That's right,
Is that
Philadelphia.
Does the Fields Institute have some role in that?
Not directly. Well, we do help to support the Fields Medal, and that's one thing. And we'll be certainly connected with it. We'll be having activities here, which are satellite conferences of the International Congress, and I'm sure lots of people will be going to it.
Yeah, good. And the public, if they're interested in finding out more about the Fields Institute, obviously there's a website. I know you have, and I've signed up for it. The public can attend seminars or talks. Is there any other way for the public to become involved in the Fields work?
Well, so as you said, there's our bi-weekly newsletter in which we say what kinds of things are happening here, and everybody is welcome to attend events at the Fields Institute, and you can just look on our website and see what there is and say that looks interesting, and I'll come. Otherwise, we have outreach events for schools especially and teachers. So we have a program called Ask a Mathematician, where we have virtually a mathematician will go into a school classroom and just talk about what they do, what mathematics is, and a way of giving children and teenagers a sense of mathematics, or being a mathematician is something that they could do. I think that that's a great program for teachers to look out for.
Yeah, I hadn't heard of that. I'm wondering what kinds of questions the kids would ask, and trying to think back to myself at that age. And so these are elementary school?
We do both elementary and high school. It's a little bit more targeted. We'll have a mathematician who, for instance, might know something about fractals. We'll go in and show pictures of fractals and talk about them and talk about things that you can do with them. And then the questions become, the Ask a Mathematician questions become more targeted.
Yeah. Okay, and the Fields Institute is a charity, so the public can support it financially.
That's correct,
Yeah.
yes. And indeed, if anybody's interested in making donations, we're very happy to receive them.
Excellent. Well, it's been great talking to you about the work that you do here, and really interesting to follow what comes out of the Fields Institute, and looking forward to talking some more.
Thank you, James. It's been a pleasure.
Great. Thank you.
Our thanks go to today's guest and to you for listening to the Quantum Feedback Loop. Please subscribe to this podcast wherever you get your podcasts, and don't forget to check out the Quantum Record at thequantumrecord.com. The Quantum Record is a monthly journal of philosophy, science, technology, and time, where you'll find the latest developments in our rapidly evolving technological world.